The purpose of this film is to describe some of the nuclear weapon effects on military systems and the research being conducted to determine and predict these effects. An example of a ballistic missile attack will be used to illustrate how different nuclear detonations affect radar systems. In this attack, 3 re-entry vehicles are deployed in line against a target defended by a radar and interceptor battery. The first re-entry vehicle is intercepted with a high-yield warhead at an altitude of 250 kilometers. Radar tracking of the remaining re-entry vehicles is predicted to be degraded by signal absorption in the ionization of the defense explosion. So, interception of the second vehicle must be made at 100 kilometers altitude to allow for a reasonable tracking interval below the first burst. Because of the degradation of tracking by the ionization of the first 2 bursts, no further high-yield intercepts can be made. So the third re-entry vehicle is assigned to a smaller interceptor carrying a much smaller warhead, which accomplishes the interception at an altitude of 20 kilometers. The effect of these explosions on the atmosphere is a major research area. This is a plot of contours of constant mass density of the atmosphere. The movement of these contours will show the changes in atmospheric density that are predicted to occur as a result of the first 250-kilometer multi-megaton explosion. These curves have been calculated with a 3-dimensional magnetohydrodynamic computer program which treats the neutral air and the ionized air as coupled fluids. It solves the physical and chemical state equations for a large number of individual packets of burst-disturbed air. This, of course, requires a very large computer and extensive computation time for each case. This lofting of relatively dense air to very high altitudes has been termed atmospheric heave. The high-altitude explosion has deposited X-ray and ultraviolet energy in the upper atmosphere. Also, high-velocity debris was guided down the field lines from the burst point. This kinetic and thermal energy heats the atmosphere in the vicinity of 100 kilometers, causing it to heave upward to achieve pressure equilibrium. This upward heave significantly changes the mass density and chemistry at high altitudes. A second burst in the same region would be detonated in an atmosphere altered from its normal state. The effects observed from the second explosion would therefore depend on the location, yield, and time of the first explosion. In addition to examining the changes in mass density of the atmosphere, this computer program is also capable of predicting changes in electron density and modification to the Earth's magnetic field. Here we are watching contours of constant electron density for the same explosion, which mark regions of radar signal interference. The magnetic field is excluded from the early fireball because the gas is a highly conductive plasma. As the gas expands, the magnetic field is distorted and regions of high magnetic pressure are developed. The ionized gas tends to flow along the field lines. The drastic upward movement of ionization seen here is the result of 2 effects. First, the transport of ionization up the field lines due to rise of the hot gases, and second, an apparent movement due to loss of ionization at lower altitudes as a result of recombination processes. These calculations of weapon phenomenology and atmospheric response are only a first step in predicting effects on a military system. Results such as these are incorporated in other computer programs which predict system performance. The RANK computer program is currently being revised to predict radar effects from field alignment of the higher altitude ionization. This results in filament structure, or the striations so frequently seen following high altitude explosions. Theoretical and experimental research is being conducted to understand how these striations are formed and to determine the severity of their effects on radar systems. One of the objectives of the CSEED program, conducted by the Defense Advanced Research Projects Agency, was to attempt to simulate the environment of nuclear striations. The CSEED program involved the release of vaporized atomic barium at high altitudes. The neutral barium cloud gives off a pale green light. Some of the atomic barium vapor is ionized by the sun, and the ionized barium radiates at a different optical wavelength, seen here as a rose color. Hence, we can see optically the separation of the neutral atoms from the ions as a result of high-altitude winds and electrodynamic forces. During one of the CSEED experiments, a target was tracked by an FPS-85 radar as the target moved behind the ionized cloud. You will see the actual radar tracking data superimposed on this photograph of the barium cloud, showing the striations in the ionization and the effects of these on radar tracking. In the following sequence, the dot represents the target location in azimuth and elevation as measured by the radar. The area of the circle represents the measured target cross-section. A circle of this size represents the unperturbed cross-section. The solid line is the actual target trajectory, determined later by ballistic interpolation. The circle and dot both display angular perturbation, and the circle also displays apparent cross-section fluctuations with a dynamic range of 40 dB. These effects were caused by a small cloud of relatively low electron density. The fact that a nuclear cloud could be from 1 to 2 orders of magnitude more dense and much larger emphasizes the scope of the problem. These angle errors represent location errors averaging 4 kilometers at the range of the target. Disappearance of the dot means that the apparent target cross-section, that is, the relative echo efficiency of the radar, has dropped below the radar's operational threshold. This is not a simulation. These are the actual experimental radar tracking results. Multiple propagation paths that result from scattering in the cloud, normally termed multipath, and reflection from the cloud, affects the radar both before and after the target passed behind the cloud. Military communications must be rapid, accurate, and continuously available. Present command and control systems use various combinations of both civil and military communication networks. These networks use radio and are therefore potentially vulnerable to disruption by high-altitude nuclear explosions. For example, the operating characteristics of modern communication satellites are similar to those of the radar system already examined. Because of this similarity, their operation may be degraded by similar nuclear phenomena. The satellite uplink is somewhat less vulnerable to absorption than a radar of corresponding power because the satellite uses direct rather than reflected energy. The downlink, on the other hand, with low available power, requires very sensitive receiving systems with large antennas and low noise receivers. However, the presence of any striations may seriously degrade the bandwidth characteristics. Most of the degrading factors present in the radar problem, then, are also important to communication between satellite and ground. Disruption from a single burst may persist from seconds to minutes, depending upon the operating frequency and other circumstances. Effects on other, and generally lower frequency line-of-sight transmissions, such as VHF, UHF, air-to-ground, will be primarily those associated with the fireball. To the extent that these paths remain near the Earth, most interruptions will be of short duration. A second general class of communication systems is dependent on the ionosphere. Changes in waveguide excitation factors and signal phase alterations may actually result in improved communications, but in an unpredictable fashion. Since the ionospheric D region is easily altered by delayed radiation from high-altitude debris, VLF circuits may be affected for many hours. In the high frequency, or HF band, reflections take place higher in the ionosphere, and the D region is strictly a region of signal attenuation. Thus, total system outage may occur for long periods of time if the D region is ionized by high-altitude nuclear bursts. Returning to the example missile attack, the first explosion blacks out all HF communication within a range of hundreds of miles. Terminals near the edge of this region could communicate away from the blackout region. System outage can persist for as long as 1 to 6 hours in the daytime. It would only last for a few minutes to as much as 15 minutes at night, except for radio paths going through the beta patch. Using the lower radio frequencies can also prolong circuit outage. The computer program that calculated the electron density shown in the first part of this film, the RANK program that computes radar performance, and computer programs used to predict communications systems performance all have a common base: knowledge of the atmospheric chemistry. Much of our present capability in modeling the chemistry of the atmosphere has been made possible by research performed under the reaction rate program. One major achievement was the successful measurement in the laboratory of two reactions of uranium with oxygen. A uranium atom combining with an oxygen atom to form a uranium oxide ion plus an electron, and a uranium atom combining with an oxygen molecule to form a uranium dioxide ion and an electron. The first reaction is very fast. The rate of the second reaction is almost 100 times slower, but still significant at altitudes where molecular oxygen exists in abundance. These reactions not only yield free electrons, but probably also produce abundant infrared radiation from the excited ions. The infrared radiation from nuclear explosions and the surrounding excited atmosphere is also a subject of intensive current research on a par with radar and radio propagation. The main sources of infrared radiation are excited atmospheric molecules, metal oxides formed by the combination of weapon debris and air, and particulate materials carried aloft by surface explosions. Thus, the source regions include the fireball, beta patch, auroral tube, debris patch, conjugate regions, widespread X-ray heated air in higher explosions, and water vapor from very low explosions, and probably atmospheric constituents set in motion in the vicinity of these regions. Radiation from any of these regions can degrade or saturate infrared detection and tracking sensors that are currently being proposed and developed. For example, airborne, rocket-borne, or satellite-based infrared systems may play a role in detection, tracking, and discrimination in a future ABM system. High-altitude defensive explosions may have an infrared image that extends from horizon to horizon. Worse, this background is inhomogeneous. Local hotspots may intermittently conceal the target, even though the region has cooled on the average below acceptable background thresholds. The degree to which infrared systems suffer degradation in this environment is not well understood. Calculations of the radiation received at an infrared detector are currently made with the OPTIER computer program. It determines total radiation intensity by performing a line-of-sight integration through the emitting region. This very brief discussion of the effects of nuclear infrared emission, compared to the previous more extensive discussion concerning the effects on communications and radar systems, does not necessarily reflect their relative importance, but rather reflects a difference in the current understanding of the two effects. Infrared radiation and its effects on infrared sensors is the subject of intensive current research. Recently, development has been initiated on a new combination computer code that will calculate the performance of both radar and infrared systems in the nuclear environment. This new code will incorporate the latest results from research on nuclear weapon effects and provide an improved capability for evaluating the strengths and weaknesses of the nation's defenses.